Next, let's talk about the variable metric technique. The variable metric technique uses variable metric proximal point method or variable metric forward backward splitting with the metric matrix M carefully chosen so that it cancels out certain terms within the monotone inclusion and thereby simplifies the computation of the resolvents. I really like this technique. I think this technique is very elegant. Let's see what it looks like. So we'll use the variable metric technique to derive the method named PDHG. We consider this primal problem where we minimize f of x plus g ax, where x is the optimization variable and a is an m by n matrix. The corresponding dual problem is maximize minus f star composed with minus a transpose and then minus g star, where the optimization variable is u. A is an m by n matrix, and this dimension m becomes the dimension of the dual variable u. This primal dual problem pair is generated by this Lagrangian. If we examine the Lagrangian, we have the convex function f, and then we have the negative of the convex function g star. F is a function of x, g star is a function of u. And then the primal and dual variables x and u are coupled, they are related through this inner product. To derive the PDHG method using variable metric PPM, we consider the saddle subdifferential operator of the Lagrangian, which has this skew symmetric matrix term plus these CCP functions. And so we consider this the saddle subdifferential operator. We apply the variable metric PPM, but we choose the metric matrix M in this particular manner. To apply variable metric PPM, it is required that the metric that we use is symmetric positive definite. The matrix M is designed to be symmetric, so symmetry is easy to verify. To verify that the matrix M is positive definite, we can use the Schur complement. So this is verified with the Schur complement. I won't go through the calculations, but this is a direct exercise of applying the Schur complement to ensure the positive definiteness of the matrix M. And when we do so, we get the condition that the matrix M is positive definite when A, alpha, and beta are positive scalars, and furthermore, alpha times beta times the largest eigenvalue of A transpose A is less than equal to strictly less than 1. So under this condition, the matrix M is positive definite, and we are able to apply variable metric PPM. So let's apply variable metric PPM and see what happens. The variable metric PPM is the fixed point iteration with this operator. So the fixed point iteration maps the iterates xk, uk into xk plus 1, uk plus 1. The first step of the fixed point iteration is to multiply by the matrix M. So given the vector xk, uk, we multiply by the matrix M. So we get so this part multiplies and gives us 1 over alpha times xk, and then this part gives us minus A transpose uk. Then in the next line, this part gives us minus A times xk, and then this part gives us plus 1 over beta times uk. Then in the next part, we need to apply this inverse. So to do so, let's add M with the saddle subdifferential. So the saddle subdifferential has this part with the subdifferential of the convex function. So that just goes here. But then interestingly, the metric M, the matrix M, and the skew symmetric component of the saddle subdifferential simplifies in this way. It's simplified in the sense that this term cancels out with this term. So here we have a 0. And then in the diagonals, we just have the identities. And then in the lower diagonal part, we have minus 2a. Now, this matrix having this lower triangular structure is essential. It is this lower triangular structure that will allow us to apply this inverse in a computationally efficient manner. To understand how it is that we can compute this inverse, we'll put the inverse on the left-hand side so that we no longer have any inverses. When we do so, we would just apply this operator to the left-hand side. So we have this lower triangular matrix multiplied to xk plus 1, uk plus 1, and then we have the subdifferential operators, a partial f and partial g star applied to xk plus 1 and uk plus 1. And then we have this inclusion. This right-hand side remains the same. So then the next question is, how do we solve for xk plus 1 and uk plus 1? Well, because this matrix is lower triangular, so because this this system of inclusions has a lower triangular structure, what we can do is we can solve for xk plus 1 first. So this system of inclusions can be understood as two separate system of inclusions. And if you look at the first line, well, the first line involves xk plus 1. It involves xk plus 1. It involves xk and uk, which are provided from the previous iteration. But notably, uk plus 1 does not enter into this first inclusion. So we can simply solve for xk plus 1 in the first line without worrying about its interaction with uk plus 1. Then to solve for xk plus 1, we simply write out what the inclusion becomes. So we multiply by alpha on both sides. And we get this. Note that here we have what would become a resolvent, so we apply the resolvent on the right-hand side. So we get xk plus 1 is the proximal operator with respect to f applied to this expression. The next line of this system of inclusions involves uk plus 1. So uk plus 1 enters this equation, this inclusion. Uk plus 1 is entered here, and then xk and uk, which are provided from the previous iteration, are utilized. But also xk plus 1 enters this inclusion as well. But xk plus 1 has already been computed. So now that xk plus 1 has been fully determined, we can solve for the now remaining unknown uk plus 1. The way we do that is we multiply beta on both sides and keep the unknowns on the left-hand side. Okay, and then this part, minus 2a times xk plus 1, that is now a known. So we send that to the right-hand side, beta a xk plus 1 minus beta a xk plus uk. So now here we have uk plus 1 on the left-hand side, and this is now in the form of the resolvent. So we apply the proximal operator, we apply the resolvent to both sides to get uk is equal to uk plus 1 is equal to the proximal operator with respect to g applied to this right-hand side. And the term that goes into the proximal operator involves uk, xk, and then xk plus 1, but xk plus 1 was computed independently previously before the computation of uk plus 1. So the linear system being lower triangular is essential, and it is that lower triangular structure that allows us to compute xk plus 1 first and then compute uk plus 1. So to summarize the result of the previous computation, we get xk plus 1 is obtained through this computation, and then uk plus 1 is obtained through this application of the proximal operator. This algorithm is referred to as the primal dual hybrid gradient method, PDHG, and it is also referred to as the Chambol-Poch method. To give you a brief history of this method was proposed by Chambol and Poch, and it was popularized by Chambol and Poch's paper. But it was later discovered that this method was proposed independently and earlier by Esser, Zhang, and Chan, and that the method was named primal dual hybrid gradient at that time. For this reason, the method is nowadays more commonly referred to as primal dual hybrid gradient, PDHG, and I will be using the name PDHG. So we derived PDHG as an instance of the variable metric proximal point method. If total duality holds, alpha is positive, beta is positive, this condition ensuring that the metric matrix M is positive definite holds, then the primal iterates converge and the dual iterates converge. Let's again briefly discuss the choice of metric that was used in the derivation of PDHG via the proximal point method. So the PDHG is derived from a variable metric proximal point method, and I guess technically speaking, a proximal point method involves just one operator, and therefore it is not an operator splitting. However, the PDHG method is a splitting in the sense that the function f and the function g are dealt with separately. Choosing the metric m to obtain a lower triangular system is the crucial insight in this derivation. For example, if we were to just simply perform the proximal point method without a variable metric on the saddle subdifferential operator, then we could write down mathematically what this iteration is. It's just this, but this method would not be useful practically, because in the linear system, the off diagonal terms will have the effect of coupling the xk plus 1 and the uk plus 1 iterates, and that will result and the consequence of this coupling is that the computation of the primal and dual variables will require simultaneous computation. And when there is no splitting, then performing one iteration of this fixed point iteration becomes no easier than solving the entire problem. Next, let's use the variable metric technique to derive the Kondrat-Vu method. The Kondrat-Vu method is a generalization of the PDHG method that we had considered previously. So the optimization problems that we consider is of this form. So for the primal problem, we minimize f of x plus g of ax plus h of x. So compared to the previous problem that we considered for the PDHG setup, the function h is newly added in. The function f and g are, of course, assumed to be CCP functions, but the function h is, in addition to being CCP, it is assumed to be differentiable. The dual problem is of this form, and this primal dual problems pair is generated by this Lagrangian. Again, compared to the PDHG setup, the difference of the Lagrangian is just the added function h. So as before, we apply a variable metric method to the saddle subdifferential of L, but in this case, instead of the variable metric ppm, we apply the variable metric forward-backward splitting to the saddle subdifferential of L. In this case, we use the same metric as before. So the saddle subdifferential of L has this skew-symmetric linear term. It has these subdifferential operators as before, but in addition, now that the function h is added in, the saddle subdifferential has this term as well. We split the saddle subdifferential of L into this part, the part that we had in PDHG, and we refer to this as just the f operator. And then we also have, and then the other part is this operator, which we refer to as the h operator. So a variable metric forward-backward splitting with this splitting, this collection of the terms, and with the metric m can be expressed in this manner. So the fixed point iteration maps from xk comma uk to xk plus 1 comma uk plus 1, and then we perform the forward step, the forward step, the gradient descent like step, and then we apply the inverse operator, the resolvent, after that. So if we consider what happens here, we first multiply m by x comma uk, xk comma uk. So that gives us 1 over alpha times xk minus a transpose uk. And then in the bottom, we get minus a xk plus 1 over beta uk. But then we also have this minus h operator applied. So minus h has no component in the bottom, but it has grad h on the top. So that gives us grad h of x added in. And then here, within the inverse, in the inverse, we have the lower triangular linear system, because this upper triangular part cancels out the upper triangular part of the metric m. And then in the lower bottom part, we have minus 2a, and then the identities in the diagonals. Now, to evaluate this inverse operation, we can use exactly the same line of reasoning that we used in the derivation of PDHG. And that line of reasoning leads us to this two-line description of the algorithm. Again, because we have a lower triangular structure in the inverse, we are able to first compute xk plus 1 and then use that result to compute uk plus 1. So in the first step, we utilize xk and uk, perform this matrix vector product and a difference, and then furthermore, we evaluate the gradient of h at x of h at x and then subtract that out. So this is the only difference. This is the only added computational step compared to the previous method, PDHG. And then after that, we apply the proximal operator with respect to f to obtain xk plus 1. And then in the computation of uk plus 1, we utilize uk xk provided to us from the previous iteration, and also we utilize xk plus 1, which was computed in the immediate previous step. And then to compute this vector, then we apply the proximal operator with respect to g star to obtain uk plus 1. This method is named Kondrat-Vu because the method was independently proposed in the same year by Laurent Kondrat and Bangchong-Vu. If total duality holds, if H is L smooth, alpha and beta is positive, and if this step size condition holds, then the primal iterates converge and also the dual iterates converge. So we derive the Kondrat-Vu algorithm as an instance of variable metric for backward splitting, and now let's establish this convergence criterion. Now note that this condition is stronger. This is a stronger condition compared to the condition that we had in PDHG. Because this is a stronger condition, this condition automatically implies that the metric matrix M is positive definite. So M is positive definite under the stated conditions, and by utilizing basic computation, basic but somewhat tedious but basic computation, we can obtain the inverse of the matrix M. So M inverse can be written in this manner. So I won't go through the steps of performing this computation, but I'm sure I'm asking you to believe the result of this computation. But if you don't believe me, then you can multiply M to M inverse to verify that this is indeed the inverse of M. And then let's define this number theta with this. And since the step size condition that was stated in the previous slide, since the step size condition that we're assuming is this quantity is less than or equal to 1, well, this condition is equivalent to theta being strictly bigger than 1. Then using the definition of theta, we have that this quantity, this matrix is less than or equal to this matrix in the sense of positive semi-definite ordering. The most direct way to verify this ordering is to consider the eigenvalues of this left-hand side and to note that this scalar quantity, so this is a scalar and it's multiplied to the identity matrix, so you can verify that this scalar identity is the largest eigenvalue of the left-hand side. And then by definition of theta, if we multiply this out, we get 2 over L times identity, so this is an equality. Now that we have established the preliminary calculations and the definitions, we are now ready to perform the convergence analysis of Kondrat-Vu. So our plan of attack will be to establish that this operator, with the theta here, is non-expansive in the M norm. This will imply, because theta is strictly bigger than 1, this will imply that this operator, which is the forward step operator used in the variable metric for backward splitting, used to derive Kondrat-Vu, the non-expansiveness of this operator will imply the averageness of this operator in the M norm. And if the forward step operator is an averaged operator, then the forward backward splitting iteration converges, and therefore the equivalent Kondrat-Vu method also converges. So let's show that this operator is non-expansive. To do so, we just directly plug in x comma u and y comma v into this operator and evaluate the M norm. Then what we do is, so here we have just the identity, here we have the operator h and M inverse applied. So we expand out the terms, so we get this term, we get this term squared, and then here we have these cross terms. Now note that this norm is the M norm, and you would expect that because we have identity, so here we have x comma u, y comma v, and we subtract that and then we have norm squared. But here we have the M inverse norm, and the reason we have the M inverse norm is that, so this term corresponds to this second part here. So we have the M norm, but we have the M inverse squared. So by having M inverse squared, one of the M inverses cancels out the M, and the other M inverse enters in here as the M norm. And then in this cross term, we don't have the M norm. This is just the regular inner product without any metric matrix M. And that's because Well, when we are evaluating the cross terms, we have x comma u multiplied to m inverse h y comma v. So this m inverse cancels out the metric matrix M, and therefore we get the regular inner product in the cross terms. Okay, so the H operator has the gradient operator for the x input, but it's 0 for the second output. So when we evaluate this inner product, the u and the v becomes irrelevant because on this part there's nothing on the second part. So this we can simplify this inner product as x minus y, inner product with grad hx, grad hy. And then here we have the H operator and then the M matrix. But note that the H operator, again, has something on the top, but has 0 on the second component. So if you think about what happens here, we will have the grad h squared, and this part, so this component is the 1 by 1, the top left block component of M inverse. Remember, in the previous slide, we wrote down the calculation of M inverse, but in the evaluation of that norm, only this top left part matters. So this top left component is what goes into here. Okay, so now that we've simplified, performed some simplification, now let's use some inequalities. So the H operator is assumed, so the H function is assumed to be a CCP L-smooth function. So we can use the coercivity inequality to bound this inner product with this grad H norm square. And then by the previous reasoning, this M norm with this metric is smaller, is bounded below with the metric 2 over L times identity. So this term is bigger than this term, and using that inequality, we can drop these two and just and conclude this. So in conclusion, we've showed that this operator is non-expansive in the M norm, and this is the non-expansive inequality that we've established, and that implies that this operator using the fourth step of Kondrat-Vu is averaged, and that establishes convergence of Kondrat-Vu. So here the high-level derivation idea is, again, quite simple. We use a variable metric method and a carefully chosen metric M to cancel out components so that we get a lower triangular form of in the inclusions, and that allows us to compute the primal update first and then the dual update next. And then to establish the precise convergence criterion, the precise step size requirement, we underwent this somewhat laborious calculations to establish when the operator becomes averaged. As a brief respite from the derivation and analysis of these optimization algorithms, let's take a look at an example that utilizes these algorithms. In computational tomography in CT imaging, the medical imaging device measures the radon transform of a patient. It is common to image the chest area of a patient using computational tomography with a CT scan, and when that happens, instead of measuring the shape of the chest itself, the device measures the radon transform of the patient's chest. For the purposes of this discussion, we can think of the radon transform as a transform much alike the Fourier transform, and then when discretized, it can be represented via the matrix M. So the discrete radon transform operator is a matrix. It's an M by N matrix, and the measurement B is the measurement that we use to reconstruct the unknown X. Usually, it is often the case that M is less than N. So in terms of the matrix dimensions, that means the matrix M is a fat rather than a tall matrix. And in terms of the degrees of freedom, this means there are many more unknowns than measurements. The measurements are related to the true unknown image through this relationship. So B is roughly equal to R times the unknown image X true. We write here approximately equal because there is always we want to allow for measurement noise. And the common scheme for recovering an approximation of the original image is to solve this optimization problem. So the optimization variable here is the image X. The image is usually a 2D image or a 3D image, but we vectorize it into a length n vector. So we apply the radon transform of the image X, and we want that to match our measurements B well. So we have this L2 penalty term of this for this reconstruction loss. But in addition, we also want the image to be to be realistically looking. And one way to measure the to measure the complexity of an image is through this total variation norm. So this penalizes. So the operator D is the finite difference operator. So we penalize the sum of the absolute values of the finite differences of the image. Why it is that the solution to this optimization problem often provides a good reconstruction, a good approximation to the unknown image x true is that discussion is beyond the scope of this class. But for our purposes, we'll just state that this optimization problem is often used to perform image reconstruction in computational tomography. In the context of CT, the R transpose operator is referred to as back projection. And the R matrix and the D matrices, they are linear operators acting on 2D or 3D images. And therefore, the matrices R and D are very large matrices, but the applications of them and their transposes are efficient. So then to solve this problem using PDHG, we recast this problem into this form. So here, this is just the 0 function, the function that outputs 0 regardless of the input. And then so we have 0 with x as the input, and then g with ax as the input. A is a block matrix with this form, and the g is a function of y and z. So the y corresponds to this block, the z corresponds to this block, and it has this form. These two functions are CCP functions that are approximable. We have a closed form solution for it. And the function of g being proximal is equivalent to the g star, the g conjugate being proximable through the Moreau identity. So we can now apply PDHG to this problem form, and when we do so, and when we simplify the algorithm comes out to be this. What's noteworthy in the algorithm is that the only computationally intensive operations are matrix vector products. So in the X update, we multiply by R transpose, we multiply by D transpose. And then the U update, we multiply by R. And in the V update, we multiply by D. But otherwise, all other operations are quite elementary. Those are just scalar products, vector addition, and here we have an element by element clipping, a projection onto the interval minus lambda over beta plus lambda over beta, which is computationally very cheap. In the context of CT, the R matrix and the D matrices are huge matrices that we should not explicitly form, but these are matrices that we can apply the matrix vector product efficiently with. So this matrix vector product can be performed, these matrix vector products can be performed efficiently without the need to directly form the matrix R and D, and the same is true for R transpose and D transpose. Because the matrices are so big, if an optimization algorithm were to require the computation of an inverse, say for example, an optimization algorithm requires the use of identity plus A transpose A inverse, then computing the inverse would be a very expensive operation. In contrast, every iteration of PDHG is quite economical, as it only relies on matrix vector products without the need to compute any inverses. Next, let's take a look at some Python code implementing the CT example. So first, let's execute the program and let it run while we go through the implementation. So this code is made available to you, so you are free to download it, play around with it, and run it yourself. But I'll go through the implementation very briefly. In the first step of the Python program, we do the necessary imports, so we import the necessary libraries for this code to execute. And then we generate the synthetic data for the true unknown image X that we wish to recover. So specifically, as you can see in the original image that you see in the execution is called the Shep-Logan Phantom. It's a synthetic image that is meant to roughly simulate a human torso in this medical imaging context, and that is the unknown image that we wish to reconstruct. This variable theta represents the angles in which we measure the radon transform. So it roughly describes the measurement matrix A in our system. And then here the sino, so this is short for the sinogram. So that's the measurement in our system. This is the B in our problem. And then we also add a little bit of noise to the measurement B. Okay, here's some plotting code. And then So we set the total number of iterations to be 1000, and then we set the value of alpha and beta to be this number, lambda to be this number. We start, so we need to choose our x0 and our u0 and our v0s. So we let the initial x image be just some random image. We let the u's and the w's, the v's and the u be just zeros. So we choose our starting points essentially arbitrarily. And then we execute our algorithm PDHG. So in our algorithm, we need to perform compute the difference 2xk plus 1 minus xk. And in order to be able to do that, we need to remember the previous iterate xk, even after we've computed xk plus 1. So this x prime is a variable that stores the previous iterate. And then in our update from xk to xk plus 1, we compute the matrix vector product D transpose V. Well, the matrix D and also D transpose corresponds to taking finite difference derivatives. So this is the computation of the matrix vector product D transpose B. And as you can see, this just amounts to shifting indices of the variable Vx and Vy, so those are the x and y components of the variable V, and that's because we're just performing a finite difference. So there's no need to form the large matrix D transpose. The matrix vector product D transpose V can be computed in this very efficient manner. And then we perform our variable update. So here we use the minus equals a compound assignment operator to compute xk plus 1 from xk and the uk and the vk variables. And note here, so this is where we compute the matrix vector product R transpose U. So this function named iRadon is the radon transform that we used in the generation of our data. So remember, we use the function radon that's for computing the radon transform, and the execution of this function corresponds to performing a matrix vector product with the matrix R. Here we are using the function iRadon, and iRadon with these particular parameters corresponds to performing the matrix vector product R transpose times, in this case, U. So R transpose times U also can be computed without forming the large matrix R transpose. So the internal workings of how this function iRadon is implemented is beyond the scope of this demonstration, but I will make clear that the matrix R transpose is not formed. Forming R transpose is a gigantic matrix. You would never want to form that matrix, but there's a much more efficient way to perform this matrix vector product. So we compute xk plus 1, and then we compute the 2xk plus 1 minus xk here and store that as x prime. And then we need to perform the uk plus 1 and vk plus 1 updates. And in the algorithm written in the previous slide, the noteworthy computation in the uk plus 1 update is the matrix vector product with the matrix R. So R times the 2xk plus 1 minus xk, that's computed here with the radon function. So radon, the function applied to x prime, that computes the matrix vector product. And then for the computation of the v variable, the noteworthy computation again is the computation of the matrix D times 2xk plus 1 minus xk. So that's computed here because again the matrix D is a finite difference matrix. So in order to compute the matrix vector product with D, we just need to perform a shift in the indices and perform subtraction, and that's it. So this highlighted component corresponds to the implementation of PDHG, and this remaining part corresponds to printing stuff and the plotting. Okay, so that's the algorithm, and as we can see, the reconstruction initially started out not very clean, but as the iteration progresses, we can reconstruct the original image not perfectly, but we can perform the reconstruction well enough that we can identify all of the features within this synthetic medical image.